Welcome back to everyone online as well. We are now into the sort of last quarter of our training, and I think one of the most keenly interesting sort of awaited sessions. We're now going to go into case studies looking at challenging situations for slope stability assessment. And case studies is always a nice way to look at how different people have done things and what we've learnt from those types of things. So the first one this afternoon is I'm going to ask Katie to talk to us about her case study on a South African tailings dam. It's an upstream tailings dam, and try and understand how you've assessed the stability using nonlinear methods. So over to you. And Katie works for ARQ, which is a Pretoria-based consulting company. Thank you.
Afternoon, everyone. I'd just like to start off firstly by saying thank you to ICOLD and to Andrew and Andy Small specifically for giving us this opportunity to present here today. We're very grateful and are keen to share some of the work that we are busy with. So as Andrew mentioned, I'll be presenting a case study of a critical state stability assessment on a tailings dam. And we'll be going through the following points. So we'll start off with some TSF details and then move on to the material testing that was conducted, and then material property calibration, and then a static analysis of the tailings dam to its final design height. And then we'll take a look at the implication of drained versus undrained behavior. So how does that material behavior differ in a critical state framework? And we'll do that through a demonstration, which is the application of an incremental load to the basin of the tailings dam. Then we'll talk about the development of time history signals, which will be used in the dynamic seismic assessment of the tailings dam, and then the actual analysis outcomes, and end off with some findings and conclusions. Okay, so starting off, we're dealing with a platinum tailings dam that was constructed through on-wall cyclone upstream deposition. It's a side hill dam with an outer slope of 1 in 3.5, and it currently has a GISTM consequence classification of high. The facility is currently 65 meters high, and it has a final design height of 115 meters. This obviously depends on the facility's performance between now and when final design height is reached. The stability assessment findings that I'll be showing are for the facility at its final design height, so we're not looking at its current condition. So we'll start off with the testing that was conducted and used as input into the assessment. And the first up is in situ CPTU testing, which we've gone through in some detail yesterday. And then lab testing in the form of critical state triaxial testing, monotonic direct simple shear, and cyclic direct simple shear tests. As Alejo mentioned earlier on, we use material constitutive models to define how a material behaves. So it's basically a bunch of mathematical formula that idealize a soil's behavior, and you would select different constitutive models for different purposes. In this instance, we've used the NORSAN model to develop the facility to its final design height, and then to look at static loading scenarios. And then for the dynamic seismic vulnerability assessment, we've used the PM4 SILT model. So I'll start off by going through the derivation of the properties used as input into the NORSAN model. And for this, we mainly use triaxial tests. So on the plot is the stress paths of some triaxial tests that were conducted on the overflow material. And we've got 2 loose undrained tests and 4 loose drain tests. and these are used in the derivation of the critical state line. We've also got some dense drain tests that we'll use to derive parameters, some other NORSAN parameters that I'll discuss in the upcoming slides. So if we take the stress points on those loose triaxial tests where critical state conditions are reached, and we plot a trend line through those points, we derive the critical state line, which in this instance was taken as a linear critical state line. You also get a curved one, depending on your material behavior and what plot sort of trends the best. So we've got a linear one in this instance, with gamma being the Y value, so your void ratio at a mean effective stress of 1 kPa, and lambda 10 being the slope of that line. Then using the dense drained tests, which are also referred to as D-min tests, we can plot the minimum dilation of those tests and that corresponding stress ratio to get those plots. So those 4 plots on the left are the dense tests. They experience dilation, whereas the ones that are plotting, the 4 tests plotting close to the y-axis don't really experience dilation. They are the loose tests. So we really rely on those dense tests to come up with stress and state dilatancy parameters for the NORSAN model. So if we plot a trend line through that, a y-intercept of that trend line gives you MTC, and the 1 minus NTC gives you the slope. And then just confirmation that you've selected the correct MTC value, if we plot the loose undrained stress paths in PQ space, so mean effective stress versus shear stress, and we can see that those stress paths converge on the critical state line, which is the black dashed line, and the slope of that critical state line is MTC. So you can see there's a fairly good fit, and that confirms our choice in the right side graph. Okay, so this is a plot that we got quite a lot of scatter for the specific material type, but it's a plot of the minimum dilation of those dense tests, and then the corresponding state parameter, which you can see is negative in this case. So we are talking about a dense material. It's got a negative state parameter. It falls below the critical state line. And we tried our best to plot a line through that scatter, coming up with chi TC, which is the slope of that line, and in this instance got a value of 12. So we've now derived all of these input parameters, and one of the most interesting, coolest ways of checking if these input parameters are correct is to actually run, I forgot about hardening. So we also calibrated the hardening parameter through iterative forward modeling. And so the plastic hardening of the material is defined by 2 parameters. There's HO and H psi. And what we can see on this plot is that the hardening modulus for the looser tailings, meaning with the tailings with a higher state parameter, that the hardening is a lot lower than those dense and dilative samples. Okay, so now getting on to the simulation. So what we actually do is we use all of those derived input parameters, we plug them into a finite element or finite difference software package, and we actually simulate the triaxial test and see how those input parameters work when compared to the actual test data. So here's various plots on this slide. We've got deviatoric stress versus axial strain on the top left. That's an important one. And then also the 2 plots on the bottom are the stress paths in the critical state 3D framework, so deviatoric stress, mean effective stress, and void ratio. So those are the 2 plots in the 2 different projections of the NORSAN model. The dashed lines are the actual test data, and let's take a look what the simulation gives us. We can see that it gives us a pretty good fit. All right, so With Norsand calibration complete, we'll now move on to PM4 silt, which once again was used for the dynamic or seismic stability assessment of the tailings dam. So this is a simulation of the PM4 silt parameters being matched to the Norsand parameters. So we're just calibrating and checking whether those two constitutive models are actually matching each other through a plane strain compression test. So the dashed line is the Norsand model, and that blue solid line is PM4 silt. So in this instance, we can see that pre-peak stress, so before that peak strength is reached, we have a very good fit with the PM4 silt model showing a slightly more brittle behavior. So the peak and residual strengths are pretty well matched, but we can see that PM4 results in a more rapid drop in strength, so it's a more brittle response. But we did try and aim on getting the pre-peak behavior to match as well as possible. Obviously, just let me mention over there that these are all sort of idealizations. They're a bunch of mathematical formula that have drawbacks and they have pros and cons, and you're never going to get a perfect exact fit. So you sort of have to compromise and aim for the material behavioral aspects that are most important to you. All right, so then a derivation of some more PM4 silt parameters, and we're going to look at two important parameters, SU ratio and NB wet. SU ratio defines the residual strength of the material, and we can see in this instance that it's not a constant input parameter, it actually varies with the state parameter, so the density of the material. And then NB wet defines the peak. So we've got SU ratio defining the residual and NB wet the peak. And we can see that throughout the model, those two input parameters vary according to the state parameter. Then to calibrate the dynamic properties of PM4 silt, so up until now we've been talking about the static properties, but there's a specific dynamic property for PM4 silt called HPO, and we calibrate that parameter using cyclic direct simple shear tests. And so the plots shown on the slide are the actual test data, and then this is a simulation of that cyclic direct simple shear test. One of the plots that we try to match best is the bottom center plot, which is the pore pressure ratio on the y-axis and number of cycles to failure. You can see this test took about 50 cycles to fail. This plot shows test data, and on the y-axis we have the cyclic stress ratio, which is the ratio of shear stress applied to the sample divided by the normal stress. And then on the x-axis we've got the number of cycles to failure. So you can see this sort of downward trend where as the cyclic stress ratio is reduced, the number of cycles to failure increases, so the load is less aggressive, and that sample can endure more cycles. And then, so we come up with this trend for HPO, like an idealized formula, and using that, we come up with the gray point shown in the slide. So you can see in some instances it matches pretty well, those points over here. And then in some instances, the trend line or the idealized HPO does result in a slightly conservative result where the number of cycles to failure is less than the actual test data. So this is just HPO assigned throughout the model as a variable input. Okay, let's move on to our phreatic surface assumptions. So we've got our CPTU results for the facility at its current height, and that results in a phreatic surface looking as shown by the blue line on the slide. And if we infer that or paste it onto our cross-section, it looks something like that. You can see it falls more or less on the interface between the underflow and overflow. And so it wouldn't be a completely unrealistic assumption to extrapolate that back at the interface of the underflow and overflow for the facility at its final design height. So this basically assumes that everything underneath the phreatic surface is saturated, and because it is contractive, it is therefore potentially liquefiable. Okay, so unlike the results through limit equilibrium or the strength reduction method or something like that, where you get like one output that's a factor of safety, that's not really possible for these deformation analyses using critical state soil mechanics. And so what we prefer to do is to look at discrete points in the model and then query their stress and state during the simulation, so during construction of the facility and then as loading scenarios are applied to the facility. So this is a stress path, a plot of the stress paths of those specific queried points throughout the stage construction of the facility, and we're looking at PQ space, so mean effective stress versus shear stress on the y-axis, with that black line being the critical state line, and you'll see the stress development of those queried points as the tailings dam is developed. They're moving up and to the right, and what is interesting to note is that these points over here, they sort of deviate from that general trend, and those points over there are located towards the toe of the facility, and what's actually happening there is that they are laterally far enough away from the application of the tailings on the tailings dam to not be affected by the vertical load, but there is an increase in the shear on those queried points. So you get this vertical movement upwards where mean effective stress isn't increasing, but the deviatoric stress is. So those are potentially the least stable or less stable stress paths, and that would be an area to look at more closely. So in the previous slide, we showed PQ projection. Now we're looking at EP, so void ratio versus mean effective stress, with that black line being the critical state line. And those exact same stress paths of those same queried points, starting on the left and then moving to the right, with void ratio decreasing as consolidation takes place as the tailings densifies. Okay, so it would be useful to quantify the stability of these queried points and the elements in the tailings dam in general. And so a way of looking at it is on the slide we've got an undrained stress path that moves to the left, it contracts, it then reaches a peak, and then it undergoes strain softening and intersects the critical state line. Instability of that stress path actually arises at its peak, and a line drawn from the origin to the peak of that stress path is the instability locus. So that's been mentioned in quite a few of the previous presentations. Unlike the critical state line, the instability locus is not a set line, and it actually depends on the state parameter and on the hardening of the material. So instead of having it'll be a set line for a specific element within that model at a specific stress state or state parameter, but it might vary throughout the simulation, and it'll definitely vary throughout the tailings dam. So let's take an idealized stress path that comes to that black dot over there. And if we look at its stress ratio in comparison to the stress ratio of the instability locus, we could come up with a measure or a way of quantifying the stability of that stress state. So as I mentioned, the instability locus isn't a set line, and as we can see over here, I'm sorry for everyone on the left, but we've got the black stars over there, so those are the instability locuses of each of these individual stress paths, and so we sort of come up with a region of instability. So if we, for example, look at that specific stress path, which has a stress ratio, which is the gradient of that blue line, And then we look at its instability point, which has the stress ratio, which is the gradient of the red line. And we look at the two in relation to each other. We could see how far undrained instability is from the current stress state. So if we take the model and calculate the stress ratio, which is the top plot over there, and then the stress ratio of the instability locus, which is the point at which undrained instability would arise, and then we take the one divided by the other, we would get the plot at the bottom, which is a sort of a factor of safety, for want of a better term, of those specific elements. So within the core of the facility over here, we can see that there's factors of safety exceeding a value of 2, and then closer towards the toe of the facility and at the base of that potentially liquefiable overflow, we've got factors of safety that are quite a lot lower than that. So if undrained conditions were to be induced, those would be the levels of stability of those elements within the model. So points drawn, the stress ratio and factor of safety plots indicate the margins of safety which would occur if undrained conditions were induced. These were identified to be the lowest at the toe of the facility, and with this information, installation of monitoring instrumentation such as inclinometers or the like could be recommended, focusing on these points. I didn't want that to start yet. Okay. So now we're going to take a look at drained versus undrained behavior. And we're going to do that and demonstrate it by applying an incremental load to the tailings dam at its final design height. So we've got those colorful stress paths. Let me just try and go. Okay, so we've got the colorful stress paths. That's the facility, the stress state of the queried points up to final design height. And then we're going to apply a load to the basin, assuming drained conditions. So we're assuming that that load is applied sufficiently slowly such that no excess pore water pressures are induced. And you can see that the black stress paths caused by the application of that load move diagonally upwards and do not come close to intersecting the critical state line, even for a very large applied load. When comparing that to an undrained scenario where we assume that this load is applied rapidly and that excess pore water pressures are induced, we see a very different story where those stress paths move to the left, hit the instability locus, and then move downwards to intersect the critical state line. So that same plot that I showed before, except now after the undrained loading has been applied, you can see the development of a slip circle, a global failure of the facility. Then moving on to the dynamic stability assessment. So this required various inputs, and we'll start off with the time history signals, which are dynamic signals applied to the base of the model, and while being applied, the stress and the state in the tailings is monitored. So a site-specific probabilistic seismic hazard assessment was conducted, and this was followed by deaggregation to determine a 1 in 5,000 year return period event characteristics. The controlling earthquake was determined as an event with a moment magnitude of 5.8, occurring at a distance of 47 kilometers from the tailings dam, and the green line shows the uniform hazard response spectra for that controlling earthquake. So we're going to take a look at that first and see what the results for that earthquake are, and then move on to looking at a seismic event with a larger magnitude. So the process followed in a dynamic assessment is first to select various time history signals. As Alejo mentioned earlier on, the more the better. So you would select representative time history signals that more or less matched the characteristics of that controlling earthquake that you want to test. Then signal matching and scaling would take place, followed by deconvolution and then baseline correction. The plot shown on this slide are acceleration versus time and then velocity versus time for one of the signals that was derived through this process. The center plot shows acceleration of the facility and bottom plot is displacement of the model during application of a portion of that seismic event. The stress paths shown here are during stage construction, as we've seen before, and then also the oscillations at the end of those stress paths are the stress state changes that are induced by the seismic event. And you can see that those are fairly, not minimal, but they don't have a large effect on the stability or on the stress state of the queried points. Then looking at acceleration, velocity, and displacement with time, we can see that at the end of that seismic event, the velocity of the queried points returns back to zero, and there are permanent displacements within the slope, but they sort of plateau and come to equilibrium. Then looking at that larger seismic event, you'll see the bottom figure over here will show the development of a slip circle. So this event or this seismic signal has got a PGA 3 times the size of the previous one, and it was sufficiently aggressive enough or strong enough to induce global failure of the tailings dam. Those stress paths, you can see the oscillations or the changes in those stress paths are a lot more significant than for the smaller controlling or design earthquake. And there were 2 points that actually fell on the slip surface, and those show movement downwards and then intersection with the critical state line over there. And similar in the EP space. Very clearly, the velocity and displacement plots deviate from zero for some of those queried points, and those would be queried points within the slip circle, indicating mobilization of the slope. Some closing remarks. So, a case study was presented of a South African tailings dam whereby various potential loading scenarios were simulated and their effects on the tailings dam were assessed. So first we looked at developing the facility to its final design height, and then we looked at the proximity of the stress state of the elements within the model compared to the instability locus. A demonstration of drained versus undrained material behavior was investigated by applying an incremental load to the basin, and then 2 seismic events were assessed, one resulting in global failure of the facility. The vulnerability assessment provided insight into potential risks associated with the stability of the facility between now and final design height, and it allows for monitoring and mitigation to be implemented. The level of the phreatic surface, which was assumed to lie at the interface of the underflow and overflow, was identified as a large contributor to the stability of the facility. And in an attempt to actively lower the phreatic surface, the design was modified to include underflow curtains which extend into the overflow basin, allowing for increased drainage. So this is just a drone photograph showing those underflow curtains. So basically the cyclone deposition extends through here, allowing for underflow to be deposited in strips within the basin, increasing drainage out of the less permeable overflow material. So as deposition continues and in years to come, and as our means of assessing tailings becomes more accurate and realistic, stability assessments similar to this will be conducted, and if needed, the design of the facility adjusted, or in a worst case scenario, the deposition curtailed. The key to ensuring the soundness of a vulnerability assessment such as this involves obtaining quality information, so from in situ testing, lab testing, and all other input data, verifying the accuracy and representativeness of the analytical methods and modeling, as well as considering credible and realistic loading scenarios. This tool now allows us to analyze complex and potentially critical situations to enable us to provide appropriate engineering solutions where possible. We hope to have successfully shared some of the uses and insight gained through the correct application of critical state models in TSF stability assessment. Thank you. Thanks, Andrew.
Thanks very much, Katie. Isn't that good work? Isn't that encouraging to see what you can do with some of this deformation analysis? It can start to inform your decision making and you can start to take early action. To me, that's the takeaway from this. I'm sure you've got questions, hold them. We're going to have some questions later, but I'm sure you've got questions as to some of the details and some of the things that were done. Please, if you don't get a chance to ask the questions in the session, please speak to Katie or Thomas afterwards. But I think this is the right sort of direction, right sort of approach to how we deal with some of these cases. We're going to ask Alejo to come up and give his case study now, also on a South African tailings facility, and we look forward to hearing what you've done and how you've done it. Thank you.
Can you hear me? Yes. Yes, okay. So back again. I have this. So I have a short presentation, few slides, of a case, a very interesting case, of the application of deformation modeling when the factor of safety is not met. And I'm not going to elaborate on the details because I already have 1 hour on stage here explaining how we do these things, but I will talk a little bit more about the interaction, how we got to do what we did and what the results, the outcome was. So let's place the statement of the problem. We have a ring, upstream raised TSF, 55 meters high, which does not comply with factor of safety requirements. What you see at the bottom is one of the sections in the finite element model of the dam. What is that 4 meters? The capillary rise. What is the rainbow? The very narrow zone between saturated and dry behavior. What is that phreatic surface? Is the result of a very complicated steady state flow analysis that I will comment a little bit in the next slide. So we have a factor of safety drained of 1.70 to 2.15. This number informs us nothing. There is no value behind them. If it were 1.4 or 1.6, I wouldn't have changed any of my thoughts about this particular facility. This is a relic coming from conventional soil mechanics of natural soils where drain behavior is relevant. For these types of problems, if we skip this one, I don't think so we'll lose a material amount of insight. This is a different thing. The undrained factor of safety for peak undrained shear strength or undrained shear strength ratio, which is not necessarily uniform across the whole dam, that is very informative because it stood the test of time. We sort of understand that if the factor of safety, when we use a two-dimensional Mongeser-Prind or Spencer limit equilibrium method, if that value is about 1.5, there is a green tick that is very important for us as a first step. I wouldn't do it first. I would usually start with the residual or post-liquefaction. In fact, critical state. That the real name for this is the factor of safety when your material reaches the critical state. So we could call it the factor of safety at critical state, which is, the jargon is residual. And in this particular dam, for the various sections that were analyzed, was between 0.39 and 1.06. So this is very informative. And it is limit equilibrium method. What is this telling us? Because there are some sections that are around 1, if you do nonlinear deformation analysis of those, they will be okay. We will do it. We will get paid for to doing this. No problem to do it. But we already know in advance that is a factor of safety for fully softened strength is 0.91, 1.06. We will be okay with the nonlinear deformation analysis. It's a very rare case. It has to be extremely brittle material for this not to be the case. But with 0.39, you can start buying your earthworks moving equipment because you will need to do something. There's no way that a desktop study will walk you away from this risk. 0.39, you are in trouble, you already know. So it's important to do the limited equilibrium analysis. And what we do is bottom up. We start with the bottom, so we do the thing, we inform the client there will be a buttress, and we start doing the nonlinear deformation analysis. Shall we do the intermediate? Yes, because it's cheap. The 1.43 is also interesting because it tells you that if nothing will, if we can prevent those trigger or destabilizing mechanism to occur, or we can delay them, we should be in a much safer position. So if the peak factor of safety were to be 0.8, then we have a problem with the data. I mean, the dam is there. Okay, you see the picture in the cover. We cannot have a factor, undrained peak factor of safety of very low and 0.39 for the post-peak or the residual case and have the dam there. But this is something that can happen, and in fact, it is a result that is important. But I will elaborate more on the residual factor of safety, because how do we compute that? We compute out after an undrained shear strength ratio, and that is a lot of a discussion around this in this particular case. So do we need a buttress? 0.39, yes. How big to be decided? How can deformation modeling support our decisions in this particular case? Before we start, we need to understand that all the analysis, all the design, all the outcome, all the decision-making was driven by one key decision made early on in the process. It is, in the lack of better knowledge, compute the residual undrained shear strength or undrained shear strength ratio using Olson and Stark 2003, which in this particular case resulted on a residual undrained shear strength of 0.04 times the vertical effective stress before the shearing is applied. Thus sigma prime V0. So we start with a K naught of 0.6, which is Q over P prime of about 0.54. That is for triaxial compression. So the instability line in triaxial compression with these parameters, we already can compute them, and you will get to be 0.73, the instability line in triaxial compression. But that dam is not a triaxial compression problem, it is a plane strain problem. The instability line in plane strain is 0.60, and we are starting with 0.54. You know what it means? It means that the instability line in plane strain is very, very close to the K naught line, which means that even points that are far away from the slope can easily come across the instability line. So you do some element test simulations, and to reproduce both the peak and the residual undrained shear stress ratio, both of them are input parameters to us. We were provided with those, it was not part of our elaboration. And this is the brittleness that you get with for a range of confining stresses. In this case, we use HSS constitutive model. HSS, hardening soil model with small strain plasticity. Why not North Sand? Because North Sand is a physics-friendly, very well physics-supported constitutive model, and you cannot reproduce both a peak and a residual targets that are not conversant to each other. So you cannot tell me North Sand and 0.21 and 0.04. We cannot do that. So pick a choice. Do you want 0.21 and North Sand, 0.04? We will do our best. It will end up in 0.09 or something. Do you want 0.09? The 0.21 comes down to 0.18. Do you want both? Leave out north sun. You need something with more keys in the piano? And HSS has all those keys and can do the trick. For fully undrained deformation modeling, it can do the trick. And so we chose this particular constitutive model for this problem. Is it the best model? Yes, in this case. How come I can do everything else without choosing a constitutive model that would be able to have this flexibility? Is this the best constitutive model in all cases? For to go say no. No, it's only when it applies that you use it. So moving forward, you must get a stress field that will be sort of relevant for your analysis, which means the K naught far from the slope and the full sigma 3 divided by sigma 1 ratio, which is what is plotted here, should be realistic or more or less make some sense. So I put these two plots and the instability line for plane strain indicated in the right, at the right in the bar chart. So that is 0.60. So it's when it changed from green to yellow. So green is okay, yellow is not okay, dark green or light blue would be much better. So that is it. So we are very, very, very close. Not just on the potential failure surface throughout the model. Why? Because the instability line is an outcome of the choice of the peak and undrained strength. So if you pick 0.21 sigma prime V0 or 0.04 sigma prime V0, the instability line is an outcome. You cannot also pick that. And it happens to be very close to the K naught line as we calibrated it. So we start from here, and now we have the problem with the water table. In this particular place, we need to match the dissipation test because we have a lot of dissipation test data, and we use that to match the phreatic surface. And we have the capillary rise, those 4 meters, and we can calibrate to match those using the dynamic pore pressure U2 from the CPTU. You might remember the presentation by Andy yesterday. And now the challenge, we have a vertical hydraulic gradient of 3.5 kilopascal per meter instead of 10. So in hydrostatic conditions, it could be a 10 kilopascal per meter vertical gradient. It's not the case. It is about 3, which means downwards flow as we speak. But at some point, we need to freeze that flow from happening to do all the undrained analysis, because if you have downwards flow, this flow is draining. So you can do it, but it's much more complicated to run and trigger analysis while you have this transient flow. So we had to trick the software, changing stuff as the compressibility of water, the unit weight of water, a lot of things that we had to do to get to match the 3.5 kilopascals per meter of vertical hydraulic gradient. And again, repeated, the narrow zone here is the unsaturated behavior, which matches the experimental saltwater characteristic curve, but that doesn't matter because we tried with a wide range of different saltwater characteristic curves, and you don't get any material difference in the outcome of the study. Enough with this. So the vulnerability analysis that we did. What you will see now is not totally coherent and conversant with what I exposed 1 hour ago. Because 1 hour ago, I showed you what we think today, after running 20. By the time we did this, we had run 4 or 5 of these particular cases in this particular, we would say, region of the world. And we were picking different triggers, different to what we do now, because we were very, very impressed by the Barcelona report, and we said we need to address this spontaneous liquefaction thing. So one of the 3 triggers that I will show you is not other than spontaneously liquefying a cluster within the dam. So let's go to it. First, the configuration is the current, and that is without a buttress, and the phreatic surface is what is the realistic for the site, and the triggers are a load up there. Trigger B is a liquefied cluster, and we will increase the size of the cluster, of the liquefied cluster, until the thing comes down. How do we liquefy the cluster? We just switch the constitutive model for one which is just the unranged strength relevant at that site. And the third one is a displacement at the foundation. So that is the current configuration, and you see the difference between the first and second pictures is the buttress placed on top. So it's the full buttress. And the third one is, as analysis, is a walkaway floated beach. Our case here, can you see the difference in the phreatic surface between number 2 and number 3? What we were trying to prove back in those days is, with this buttress, even if you flood your dam and create a pond, the triggers will still be satisfactory. You will not have a dangerous situation, which is kind of indeed walk away. Far more what is expected. It was a kind of a easy to do extra exercise. Don't think about this third condition as something which is relevant for practical engineer, but because you have the mesh, you have everything, you just raise the phreatic surface and see what happens. Okay, and the actions. The load on the crest, at the crest, sorry for the English, the spontaneous liquefaction of the cluster close to the toe of the dam, and a displacement imposed at the toe of the dam. I did not need to elaborate a lot of what each of these means, because I already spent 1 hour talking about this before. And that was for the static analysis, the flow liquefaction. For the seismic analysis, we followed the procedure that I just explained some time ago, and it's about picking a number of ground motions that will all of them fit within the seismicity of the site as it was provided to us. So essentially, if you are going to pick a number, in this case PGA 0.33, for a return period of 10,000 years, but it's not just PGA, that is one of the intensity measures, it's also iris intensity, a number of other things. Okay, now let's calibrate PM4 sand. The very large circles, black circles with a yellow color in are very painful test results that we used in a previous study very close to this one, and those were provided to us, and those three big circles with the yellow inside created sort of a huge problem with a big buttress required, because those were extremely poor performance. Extra tests done with this more or less the same tilings, more or less the same density, are the red dots. These belong to this particular site that we are studying today. And you can see that if we had back in those days when we did analysis for the three yellow and black, if we had the two nice red circles that we see there, it would have been a completely different outcome of that study. So remember that the quality of that data, in this study, the 0.04 to be challenged. In the previous one, the cyclic direct simple shear test, where the quality of the data or the decisions made when you are deciding the data that is going into the analysis will play a major role. But back to our study, look at the orange and the red circles in the right-hand figure to see the calibration of PM4 sands for the seismic analysis, and look at the critical state line that is default in PM4 sand, green dashed curve. You don't stay with the default parameters of PM4 sand unless you can, which is not always the case. In our case, we use critical state line data from undrained isotropic compression tests, drained isotropic compression trajectory tests, all these trajectory tests, and cyclic direct simple shear. And you see that the critical state line of PM4 was moved out of the default value. So it's the solid black line, which is, I would say, compared to the data that is there, it's maybe closer. And then the best fit following that black curve that we could find is a state parameter of about, and there is sensitivity analysis around this, of about plus 0.10, which is the yellow solid line there, going more or less between among all the data points. And with that calibration of PM4 back to the right part of the figure, and you see the results of the calibration of PM4 compared. Please just look at the red and orange circles and leave those bad black and yellow circles out of your mind for a while. And you see that our calibrations falls on the conservative side, but not so much. Okay, so now on the left-hand side, up on the left-hand side, you see the calibration of PM4 and the number of cycles in orange that you get compared to the performance of the real test. CSS03 is the name given by the laboratory for that particular cyclic direct simple shear. It doesn't look well as a match. In fact, it's not that bad. Top right is exactly the same information, but at the left is plus to minus 5%, and on the right is plus to minus 0.5%. It's the same data with a different scale. And you see that for the first quite a lot of cycles, the matching is not that bad. It is true that if we happen to have a ground motion that will create 1, 2, 300 cycles, the difference will be significant. But now, back to the experimental result, we cannot take that as the fundamental truth. It's also the result of one experimental test. If we move to the lower part of this figure, you'll see that the shear strength with the number of cycles goes more or less very well until 8, and then there is a significant difference between what we see in the laboratory with respect to the simulation, but with the induced force pressure, which is bottom right, the difference is not that large. Displacement, and this is the results obtained. We're coming close to the end of my presentation because I will only give you a couple slides with the results. So these are the displacements obtained at the top of the buttress and at the crest for all these 20 ground motions. Let's move to the top of the crest, which is right column, and let's focus on the horizontal displacement, which is the top figure, and you see a lot of results, and you see that the biggest, the highest is about 0.25, the smallest is about 0.10 or something, and the average is 17 centimeters or 0.17. So you get values between 0.10 and 0.25. If the stakeholders will say, we found 1.25, we will use that value. I will push back and say, we can run 100 other earthquakes. I can guarantee you I will find one earthquake that will bring you to more than 0.25. It will happen. But with these 20, you already know that one may be that bad, but a bunch of them are in the range of 0.20. If you look at the full thing altogether, you may say, this displacement due to the earthquake is about. And the about is technical in this sense, about 0.20. Well, bottom is the bottom part of the right, the right side of the figure is the vertical displacement, 9 centimeters as an average. So you see, we are in a very low seismicity region. The same dam in Peru or Chile would have a totally different result, but here it's is okay. And now we go to the results, back to the results of the study, including flow and seismic liquefaction. And those are the results, which means that the current dam would not stand a high phreatic surface or a spontaneous liquefaction. So of the many triggers that, the 3 triggers that we tried, this idea of a spontaneous liquefaction of a cluster would bring the dam down. Is that realistic? We don't know. We don't know. Look, we're talking about 7.5 square meters in the mesh or cubic meters per meter, but along the entire thing. The truth is that because liquefaction is inducing propagation of pore pressure, you don't need much of an initial volume to start a propagation. So it's an indication of where you are sitting, and this is related to the factor of safety of 0.39. These 2 things come from the same sources. And remember, all this controlled by the 0.04 USR. Okay, then with a small buttress, very small buttress compared to the final one, is enough to satisfy the risk tolerance during operation. And if we do build this big full buttress here, we end up with a residual factor of safety of 1.03. It's still less than 1.1, but look, there is no way to kill that dam. Even with this 1.03, which is less than 1.1, you flood the dam, you create a pond in the entire beach, and you still don't see any trigger to failure. So these are the results of the study, and the next slide would be the first one from me without a figure on it, because it's not mine, it is from the EOR, the guy who has to sign off, okay? I will read. For what is coming next is not mine. So, the TSF initially indicated potential brittle behavior and substandard factor of safety against residual conditions. An emergency buttress was designed using limit equilibrium methods. The nonlinear deformation analysis of the geometry designed using limit equilibrium method assessed the sensitivity, which means the vulnerability, and the triggers of the reinforced configuration. It was found that there was a low probability of triggers to happen, along with an increasing limit equilibrium method factor of safety because of the steady phreatic surface decline, remember the vertical gradient, and the partial buttress construction, and this enabled the buttressing to be terminated prior to a full emergency design extent. I need to read that again. Out of the nonlinear deformation analysis, they stopped buttressing. They buttressed to a given height, and they understood that with this height, the risk of this thing going down is tolerable, and if you run the residual factor of safety, it's still not 1.1, but if we had started with the configuration with the partial buttress, and we had run the flowchart by CDA, we would have come to the conclusion that the triggers to failure were not plausible, and we wouldn't have started with a buttress anyway. So a small buttress was considered enough. So international review, both internal and external, and they peeled us off, really. It was not an easy review. Plus, ITRB input gave confidence to the EOR to stop the buttressing through a vetting process. Oh, this is a nice outcome of where a nonlinear deformation analysis was helpful in making a decision and supporting a decision in an operation, in one of these operations that really needs these kinds of decision-making process. This is it. Thank you.
Welcome back, everybody, and thanks for being on time, getting back. This is the final slot, final session. It's really encouraging to see the energy in the room and the fact that you've all stayed. I think that speaks well to to the interest that there is here and also the importance of what we're talking about. So thanks very much for staying. I think that's encouraging. For those of you online, I've also heard good feedback from the organizers that there's a good 30 of you still online. So hopefully you can stay with us, and we're going to have Andy Small speaking to us shortly as well. And I'm not sure whether he's been up all night or whether he's managed to get some sleep. But first of all, Paul is going to bring us another case study, one from North America, also an upstream tailings dam with some seismicity. So I think that'll be of interest as well. And then we'll move into Andy's presentation after that. Thanks very much, Paul.
Okay, thank you. And I'm going to set the expectations again. It's not going to be like Katie and Alejo's. They blew me away. I'm not a modeler. I did models many years ago, and I'm a little more practical. Not that what you did wasn't practical, but more applied, shall we say. Okay. So this is a case study on an upstream method TSF in a moderate seismic setting. Oh, that didn't work very well, but if anybody's ever watched the Law and Order series on TV, which is one of my favorite shows, they always begin with this disclaimer because all of their stories are taken out of the news, but they change the facts to protect the innocent. So think about that. This is actually based on real conditions, but it's a little bit of a combination from different projects to, again, protect the innocent, but also to demonstrate the methodology. So the main purpose of this case history is to walk through the application of that flow chart. So it's kind of part 2 of my first presentation. But it also has some kind of relevance in terms of it's probably could bear some similarity to some of the upstream method TSFs here in Southern Africa, perhaps with a higher seismic load though. So this is a copper tailings dam, or a copper tailings mine. The ore body is granitic diorite, so there's a bit of, or granodiorite, there's a bit of quartz sand, so we get good, fairly coarse tailings with pretty decent segregation. That results in pretty good drainage conditions. It's a reasonable raise rate of about 3 meters a year. It does have an extreme downstream consequence. The earthquake is moderately sized, again, a little bit maybe higher than you might normally see in Southern Africa. For a 10,000-year earthquake, it's a 6.5 magnitude. This is a floating earthquake, so it's a little hard to determine the distance. There is a fault that's fairly close, but ultimately leads to a peak ground acceleration of 0.22 g, which is kind of on the, if you think about from liquefaction evaluation, it's kind of on the borderline of what might be triggering liquefaction. The downstream slope is about 3 2/3 horizontal to 1. Currently has a height of about 60 meters at the maximum section, and it has very long beach width. So I forgot to include this, but average rainfall is less than 30 centimeters. So it's relatively dry. It does have, kind of a seasonal rainstorm, that rain period that occurs in the monsoon season. This is a typical CPT profile, pretty standard output, in this case from the geologismiki or whatever. I never can say that word right. And so we have tip resistance, friction ratio, sleeve friction, the soil behavior type from Robertson, QTNCS. We are typically using the Robertson interpretation approach. The SU over P for yield or peak and residual comes from the chart at the upper right, which is Peter Robertson's correlation for residual strength, which is based on case histories and is kind of inherently a fairly conservative interpretation of the historical case histories. It's something he actually shifted downward. We've talked a little bit about some of our correlations with residual strength are pretty conservative, and that's it's appropriate to start there. And I appreciated the way that the approach that was taken by Alejo on his case history is at least you want to start with a fairly conservative interpretation. As you can see on the modified soil behavior type chart at the lower right here, most of the data points for those CPTs plot below that dilative contractive boundary, so they're all mostly contractive. The ones that are dilative are typically up in the unsaturated zone. One of the challenges that comes to play in trying to select a representative value is this recognition, and I think a couple other slides have been shown of the highly layered nature in most hydraulic fill tailings, and this is I call it microstratigraphy. It's something I like to do, is to take a Shelby tube or perhaps a Dames and Moore sampler, something, or a continuous sampler, and cut that in half and then log the layers, and then you use that to select representative values. And we almost always will find a coarse tailings, a fine tailings, and then something that's in the middle, and that is reflected. And you can see within just a few centimeters that you can go from quite a high fines content to a reasonably low fines content. And so picking a value to represent the tailings is quite challenging, and I actually like the approach that Alejo was introducing from the Eurocode. That makes a lot of sense to me, is to really kind of divide it up into different zones where you reflect the shear plane crossing these layers, versus in a horizontal failure mode, you would typically follow along the weakest link. And so this is an interpretation of, this is our data set. You have a fairly nice normal distribution here. Little bit skewed, but it's pretty close to normal. And you can see the 30th percentile value, 0.3, 20th and 10th percentile value, median and the mean. So if you took a 10th percentile value, if I do this again, I probably will show a 5th percentile as well to pick up from Alejo's presentation and approach. And then, of course, kind of the most important one to me is the residual strength characterization. Now here you'll see a bit more skewed, so it's more of a log normal distribution of the data set, and you can see the parameters that were interpreted from that data set. And if we look at the 30th percentile, which we may have time to talk later, maybe in the Q&A section, about what is an appropriate value to select. But anyway, if you take the 30th percentile peak strength and the 30th percentile residual strength, you get a brittleness index of 0.67. So this is indicating that our material is highly brittle, or it's a case 4 type situation. This is laboratory testing results, and these, of course, were reconstituted to a loose state. So you would anticipate that they would shear in a brittle manner because they're prepared loose of critical state. And again, this is real data from a real project, not necessarily the same project that conforms to the geometry. But what you can see over here on this, plotting this on that ICOLD chart, the black line is a normalized value of that stress strain curve. Sorry, that one down at the bottom. So that little tiny stress strain curve right there, when you plot it normalized of peak strength divided, shear stress divided by peak strength, you see it fits that very brittle behavior. So it has a very low peak strain, probably around 2%, and then it rapidly drops down to about 80% strength reduction, or a brittleness index of 0.8. But then what you do typically see is that with increasing confining stress, you see it moving more towards a more ductile response, which is encouraging. So We do have a range of state in situ. We certainly have some zones that are fairly loose of critical state that would have a high state parameter. And then we would trend down closer toward potentially some that are dilative in the negative range and or say right around 0. Okay. Here, limit equilibrium analysis results for the post-liquefaction or the residual strength case. And this is done using a 30th percentile value or an SU over P of, or SU over sigma V of 0.1. And so in this case, this would match a case 4A in the ICOLD chart, in the flow chart, because we have contractive materials present. They are strain softening. Our brittleness index is high, as it's greater than 0.4, but our residual strength factor of safety is greater than 1.1. In this case, it's 1.2. So for this case, we breathe a big sigh of relief, and we feel good about our tailings dam. Now, if we used a 10th percentile, or what I would call a near lower bound value, we do get a different result. So we're less than 1.1, we're right at 1. So this is either a potential case 4B or case 4C, depending on what the downstream consequence is. In our case history here, it's extreme consequence, so it's a case 4C. So it really is one of those very difficult type of situations that you find yourself in sometimes, is trying to decide what's the right course of action to take here. So just to kind of walk through the application of the framework here. So yes, contractive soils are present. Yes, they're strain softening. The post-peak strength loss is greater than 20%. The soils are highly brittle. The brittleness index is greater than 0.4. Factor of safety is greater than 1.1 using the 30th percentile. And so we have a case 4A. As I said, it's generally judged to be safe or reasonably safe in the Canadian context, maybe. If it was in a low seismicity area, we probably wouldn't worry about anything else. In a high seismicity area, we would still need to look at deformations, because even though static liquefaction isn't a concern, you could have enough deformation in your seismic loading to cause some concern, depending on how much freeboard that you'd have. So you'd want to do your, certainly at a minimum, do simplified deformation analysis using Brahe-Traversaro and Brahe-Macedo, whichever would be applicable to the actual seismic source. Or you may want to do a nonlinear deformation analysis. I would tend to do that myself, and that's actually what we did in the case history. But what if, using whichever value, 10th, 5th, 20th, 30th, whatever value, if we have this case where we're in case 4C, where we have a factor of safety that's less than 1, what would we do? So first of all is, what level of confidence do we have in our residual strength characterization? So if we're using a very conservative residual strength, which would be appropriate for kind of a screening analysis, we might want to say, hey, should we spend some more time doing better characterization of our residual strength? So if we might need to go back out and do some more CPTs. We might need to do some laboratory testing. We might want to do a critical state analysis or critical state line and use NORSAND and do the type of advanced analysis that we were just looking at in the previous case histories. If we're right around 1, the chances are that we can do an advanced analysis and demonstrate that the performance will be acceptable and that deformations will be under control. So if we're in that situation, we probably would feel justified in doing more work. And in our case history that this is primarily based on, it's exactly what we did, is we actually did have a couple sections that were in the range of 0.9 to 1. And so if you're kind of hovering around that factor safety of 1 between, say, 0.9 and something less than 1.1, I think it's almost always justified to do more investigation and more advanced analysis. If you are significantly less than 1 and you have a potential loss of life downstream, that's the hardest one to solve. There's no prescriptive answer. It probably means that you still need to do some more work because you'd need to understand that vulnerability is what's the likelihood of a trigger occurring. So you'd want to evaluate the types of loading that could cause this. If it's just the earthquake and you have and your earthquake's 1 in 10,000, you might want to run a lower return period event and say, would this be triggered at a 1 in 500 or 1 in 1,000 year, even a 1 in 200 year? So that would inform your decision, because if you have a likelihood of 1 in 10,000 of this triggering event occurring, I wouldn't necessarily just run out and start building a buttress. I would monitor, and again, would plan to do some additional work to do that. If your factor safety is less than 0.5, you probably need to do something. That could be curtailing activity, that could be initiating a buttress construction. It might involve, depending on where you're at, relocation of people from the downstream hazard zone. Again, those are the really tough situations to be in, and some of you live in that area of the reality. That may be your reality. I've been in cases before where I had to kind of make judgment calls like that. It's no fun. But in this case, we didn't feel like there was a need to shut things down for the primary situation that this is based on. And so we did go back out and do some additional investigations, quite a bit of SCPTU. We did develop a critical state line and do some flak analysis using North Sand, or technically it's still underway. On the one case history that we've kind of based this on, we've improved our estimates of in situ state, which is key. We've done some additional analyses. The deformation, the dynamic analysis did not trigger flow. We are doing the same type of thing that Alejo described of evaluating different known triggers, and then also evaluating the ultimate height condition, similar to Katie's history, or Katie's case history, where you look at where it's at now, but you also need to think about what it's going to be like in the future. We did develop a buttress design. I think ultimately we're going to do something kind of similar again to the case that Alejo presented, where we'll build a partial buttress and then use observational method or performance-based method to monitor our ongoing raises over time, and hopefully can optimize the buttress. How am I on time? Okay, like 5 more minutes, maybe, okay. ALARP, I just wanted to touch on ALARP, and I think Andy might touch on this a little bit through risk assessment, but I'm sure everybody here has heard of ALARP. If you've read GISTM, it occurs 13 times. It is something that has been around for a long time in the water dams industry, and is now a big topic in the mining world. ALARP is it's actually a well-established concept, but it's not a very well-defined concept. So it's been around for quite some time. It was developed in the UK, really kind of built around the nuclear power industry. And in order to demonstrate ALARP, you need to demonstrate that accepted practice and precedent is met, that all of the societal and stakeholder concerns have been addressed, and that the incremental cost of adding additional risk reduction measures is not grossly proportionate or disproportionate to the benefit of implementing those risk reduction measures. And that last statement requires a fair amount of explanation that we don't really have time for today. But you can also just look at ALARP in a fairly simplistic, deterministic way. Certainly a lot of people do quantitative risk assessments and try to assess probabilities, and that's fine, but you can also assess ALARP by just asking, have we done everything reasonably practicable to reduce this risk to as low as possible, or low as reasonably practicable, whatever that means. So there are things that can be done, and you should be, if you're in one of these situations where you have an increased likelihood of a failure that's going to cause harm to people and potentially loss of life, you need to evaluate the different alternatives that there may be. So basically, you have three choices. You either eliminate the hazard, which is in essence to remove the dam. Many times that's not practicable. Sometimes it is. It may be a remining effort could be done to actually remove the dam. You either need to reduce the consequence, or so take people out of harm's way, and so there may be a removal of people from the downstream hazard zone, or there could be a reduction of the likelihood, shall we say, and that would be by implementing some type of engineering control. So that could be a buttress, that could be constructing a berm downstream that would deflect a potential failure. That could be some type of in situ ground improvement methodology. All the time, if you're going to be touching the dam, either through buttress construction or any type of modification, you have to make sure that the fix doesn't make the problem worse. So you can't trigger a failure by trying to fix it. So you need to be very careful about that. And certainly need to make sure that your emergency action plan is robust and exercised and ready to go if needed. But again, you know, it's important not to get caught up in analysis and what ifs instead of remedial efforts. If there's something that can be done, a lot of times the solution is actually kind of two-pronged, is let's do some type of improvement or remediation while we're also expanding our knowledge base and conducting additional analysis. And again, I've said this a couple of times, I don't envy anyone who's in a situation where you have to decide or to recommend what's the right course of action in these. So that's my case history.
Oh, thank you, Paul. I think that's a real practical approach, and I think that's really helpful in terms of guidance. I'm going to call on Andy Small to then take us through another case study, a very interesting one from North America, and then to follow that on with an initiatives and risk assessment presentation that he's offered to give. Andy, are you online and able to take over? Okay, we see your presentation. Over to you.
Great that so many people are sticking with it till the end of the day. Katie and Alejo provided excellent examples of how deformation analysis can be useful, and Paul brought us back to the limit equilibrium, which is very important. Dr. Morgenstern has been a primary advocate of the performance-based design. We're seeing the fruits of that develop with the new technologies we have and the approaches we have. At one point, Dr. Morgenstern said, you know, limit equilibrium is fundamentally going to be replaced by performance-based design. Alejo said the same sort of thing earlier, and that may happen in time, but right now, the limit equilibrium is still playing an important role in our world, and Paul's case study was an example of how that can be used. So my case study is not as severe as Paul's. It's a much smaller scale. We're going to be dealing with a case 3 situation where there's not a life safety issue downstream. We recognize that many of the tailings dams in Africa do have life safety issues downstream of them, but not all of them do. And we also recognize that you're in a rather low seismic area. So I thought this case study might be pertinent to some of your situations in Africa. It's actually in Canada, up in the Canadian Shield, located here. And our area has been glaciated. But when the glaciers retreated, they left behind layered deposits of clays, silts, and sands that are normally consolidated to lightly over-consolidated and liquefiable. So even though many parts of Canada have been glaciated and we have really good tills in the foundation of our dams, there are many areas as well that have these packages of glacial lacustrine deposits which have liquefiable zones within them, which causes grief. Earlier in Paul's presentation, when he was introducing the flow chart, he talked about if you can avoid contractive layers in the dam fill or foundation, you should do so. We have proceeded with centerline construction on these dams, so we have taken the contractive elements out of the structural portion of the dam fill, but we had to contend with the contractive layers in the foundation. It's a small facility, been operating since 1985. It's a gold facility running at only 6,000 tons a day. It started with the initial tailings deposits over here, and over time has slowly grown to its configuration now, and it'll continue to grow over the next 10 or 20 years. We're fortunate in that the tailings are geochemically neutral. We don't have any acid generating, very limited metal leaching, so we're not having to deal with water covers. It's also in a remote area, and if these dams were to fail, they would have environmental impacts, but not life safety impacts. As indicated earlier, it's a centerline construction. This yellow is the fill that's been placed at the dam. There's rock fill berms that have been constructed on the downstream side to provide appropriate stability over these glacial lacustrine sediments. As I said earlier, we have no life safety concerns downstream, and our fair weather consequence classification would be significant. And that's because if it were to fail, there would be a run out of the tailings beach, but the run out would be limited during fair weather or normal operating conditions. The pond is well away from the crest, and we wouldn't lose a pond. With the fair weather consequence classification, we've established the design earthquake as a 1 in 1,000 annual exceedance probability with a peak ground acceleration of 0.1 g. And when I look at the seismic hazards in South Africa, I see the seismic hazard here is similar to what I see in South Africa. So that's why I thought this might be pertinent to you. However, we have to think about closure. Closure of this facility is currently planned for 2035. And this facility will be shaped to shed surface water with a vegetative cover placed on it. But this dam that I've shown here will remain in place. It'll be raised another 4 meters at the end of its operating life. So that's what closure would look like. So when we're dealing with operating conditions, we're looking at the 1,000-year seismic event. And we have used different methods such as deep soil, which is a site response analysis, which has indicated to us that the 1 in 1,000-year seismic event won't trigger liquefaction down here, but greater than 1 in 1,000 will. So first blush, okay, let's assume it liquefies. We then run the post-liquefaction factor safety, and we get 0.6. That's similar to the cases that Paul was talking about earlier and that Alejo was talking about. To achieve the factor safety greater than 1.1 for post-liquefaction, this berm has to extend out about 150 meters. Now, there's other ways that we could maybe do it with deep soil mixing, soil columns, shear keys, other things we've looked at. But the costs of those preventative measures were fundamentally prohibitive and would shut the mine down. And it's interesting. We always have to be careful as consultants in terms of taking risks. So what we did is we presented to the owner the risks that they're taking. We said during a 1 in 1,000-year seismic event, we do not envisage liquefaction occurring of these materials. You're meeting the standard of the day, but there's a potential that you could have a larger event occur, and this then could run away from you. And to handle that, you would have to build these large berms. And they made the decision to not build the berms. We need to be careful that we, as our consultants, did not make that decision. They made that decision with our input. So with that, we adopted the peak factor safety 1.5 using peak undrained strengths in the foundation silty sand. And this is now considered safe in the context of the Canadian practice. And Paul alluded to that in his comments, that in Canada, we're working on a definition of what we view as safe. It's an extension to what ICOLD is defining as safe. And fundamentally, if you can meet the loading criteria associated with the classification for the dam, then the dam can be considered safe. So even though this dam might fail in an event greater than the 1,000-year seismic event, the dam is considered safe. And that's a very important point. But we didn't ignore this. We had done extensive investigations on the foundation sediments, and I'm not going to show you all the results, but fundamentally, we were in the A to B world. And we were in the case 2 to 3 of limited strain softening or moderate to high strain softening. We were not case 4. We adopted case 3, where we looked at the minimum factor safety 1.1 for residual strength. And these are the things that Paul talked about before, and we couldn't meet that. Then with advanced characterization, NDA may demonstrate acceptable behavior, and I'll get to that in a moment. We kept the minimum factor safety 1.5 for the peak undrained strength. So now we have to look out for closure. The 1 in 10,000 seismic event is now being adopted as a pretty standard seismic event for closure considerations, regardless of the classification. And in this area, a 1 in 10,000 year seismic event would result in a PGA of 0.4 G, which would trigger the liquefaction of the foundation sediments. We're now embarking on the nonlinear deformation analyses to predict that behavior. And we're going to be using those deformation analyses to try to inform what really should be done at the end of the day. So, given that we have no life safety, we have a fair weather consequence classification significant, we're okay under the 1,000. For closure, we will look at other approaches. If you recall some of the images that Alejo showed, where you take the seismic event and apply it to the facility and then predict the deformations, I expect what we will see is something like Alejo showed, where yes, you may have some deformation, you may have some slumping, but given that there's no pond on the top of closure, those consequences may be acceptable and may not warrant the construction of massive berms. Or if berms are required, the deformation analysis will help to inform an appropriate scale of those berms. So that concludes that quick short case study.